All right. So let's continue with the next session.
Yeah.
So in HQS, we noticed that simulating fermionic systems is a typical task. So we looked into methods to map fermionic systems, electronic systems to actual spin systems. And the result of this is the HQS spin mapper. And Benedikt is like the main developer of this tool. And he's going to present our findings there.
All right. Yeah. Well, hello, everyone. It's kind of my privilege to present our spin mapper method to derive effective Hamiltonians for solids and molecules, but effective Hamiltonians that describe the systems as spin bath systems. And especially, I mean, I'm writing real solids and molecules, but the materials we're most interested in are magnetic materials, where it makes sense to have a model of a spin, of interacting spins in a bath. And the spin mapper is kind of a two-tier, two levels method. And the main aim is to go from the first principles Hamiltonian description of the system, of the magnetic material, to a spin bath model Hamiltonian description that is then either suitable to directly simulate on a quantum computer, because now we have spins, and maybe we can even treat the bath with bosonic modes, for example. That would be ideal if the device allows for that. That's one thing. But the other thing is that this system is already also nicer to do active space calculations on conventional machines with it, because we've reduced the size of the Hilbert space, and we have one part of the system that is really the active part that we're interested in, that displays the low energy spin physics. And the other fermionic modes that are far away from the Fermi surface, we can treat as a bath and maybe more coarsely. So it has two advantages. The quantum computer advantage, which is, of course, ultimately our main goal, to simulate magnetic materials on a quantum computer, but also in the meantime, it's nicer to simulate on a conventional machine. I said it's two parts, because the first part of the method is to actually identify where the effective spin degrees of freedom in this material actually sit. And the second part is then what to do once we know what these spin degrees of freedoms are. But now, the first part, what are the spin degrees of freedom in the system? So we asked ourselves, what would we consider to be an effective spin degree of freedom? Because, of course, if we have the ab initio description of the material, it doesn't say this is a spin and this is a spin. The spin is somewhere hidden in there via the spin degrees of the electrons that are present in the system. And one could then, of course, think, okay, maybe it's an orbital that has an expectation value for the occupation of 1. So there's one spin in there, and then the charge degree of freedom is no longer super important, but the spin degree of freedom of the electron is now the effective degree of freedom. And then one could think, what kind of orbitals are these typically? So in magnetic materials, which typically kind of deal with d or f orbitals, which are very narrow, and I have this kind of nice little sketch here for different types of orbitals. So they're lower in energy, they're fully occupied. We have an expectation value for the occupation of about 1, and nothing changes. They are so far away from this Fermi surface, there's no fluctuation of the occupation number. But then we might also have orbitals like this one, where we have an expectation value of 1. But that is because, let's say in the ground state, it's a Slater determinant that has contributions from Slater determinants where we have double occupation, where we have no occupation in the orbital, and where we have single occupation. So on average, there is one electron in this orbital in the ground state, but the fluctuation is rather high. So treating this orbital as an effective spin degree of freedom is just not reasonable. What we're actually interested in is, for example, this narrow orbital where we have an expectation value of 1, but also basically no fluctuation. And that is typically also the shape of the orbitals that we deal with magnetic materials, like narrow d and f orbitals. So what would we consider as an effective spin degree of freedom is something like orbital phi 3, narrow, 1 electron in there, and no fluctuation of the charge degree, of the electron occupation number. So we want to find these kinds of orbitals. And that is why we turn to another metric that is not just the average occupation of the orbital, but the local parity. The local parity is very simply defined as this -1 to the power of the occupation with up electrons and plus the occupation with down electrons as an expectation value in the ground state. This might be a bit difficult to calculate, but we can rewrite it and get this nice expression. And if you look at the expectation values that are in here, then they exactly correspond to the 1 electron reduced density matrix and the 2 electron reduced density matrix. And these we can calculate with ab initio methods, not DFT and not Hartree-Fock. So mean field methods are unfortunately out, but everything that is more correlated than that gives us access to a reasonable 2-RDM. And then we can calculate the local parity in the ground state. Still kind of the ground state from this ab initio method, but that is good enough to get a feeling for what are the spin degrees of freedom. Because why is the local parity such a nice metric to determine whether we're dealing with spin degrees of freedom? If we just look at a single kind of orbital and the 4 different basis states for this orbital, like unoccupied, spin up, spin down, and doubly occupied, if we apply this parity operator to it, then we see for the 2 states where the orbital is singly occupied, that is either up or down, we get an expectation value of -1, but we get an expectation value of +1 for the other basis states. And that also means that fluctuation around 1 will always get us away from -1. So we can't kind of average out the fluctuation and still end up as occupation 1. If there is something that is not singly occupied in character, it will always drive us away from -1. So if we find orbitals, or we find a basis where there are orbitals with local parity very, very close to -1 or even -1, we know these are very good spin degrees of freedom because there's no fluctuation of the particle number in this orbital left. And to try this out and also to kind of prove that this makes more sense than maybe traditional ways of finding such orbitals, traditional meaning kind of the lived-in natural spin orbitals, where you would calculate the 1 electron reduced density matrix of the system in the ground state, diagonalize that, and then take all the orbitals that correspond to an eigenvalue of 1. We wanted to test this, so we thought up this very simple toy model, which is just a tight binding chain, and attached to each tight binding chain via a small hybridization are these orbitals where there's a strong Hubbard repulsion between the electrons. So this is really just designed to have a toy model where we know we have actually good spin degrees of freedom, which are these B orbitals, because there's Hubbard repulsion, so there needs to be only 1 electron in there, and they're also very weakly coupled to the rest of the system. So kind of just from the get-go, we know these should be kind of spin degrees of freedom. And then we try out these lived-in natural orbitals. We calculate the ground state of the system, calculate, by the way, here are the local parities of the basis orbitals, because we designed it so that the B orbitals are spin-like, and we see the B orbitals have a parity of pretty much -1. But then we do the lived-in natural spin orbitals, and ta-da! The natural orbitals all have parities from 1 to a bit above 0. So these are basically either completely empty or fully occupied, and these are massively mixed. None of them are good spins. So if you try to find spin-like orbitals or effective spin degrees of freedom, I will use these words interchangeably. With the traditional method, for this toy model, you will fail miserably. And if you fail already miserably for this toy model, then there's no reason to rely on it in general. But we can start in this awful basis and look at the local parity and optimize that. So do basis rotations, always trying to optimize the local parity. And then we end up with this purple line here, which is basically just the original basis just reshuffled. So we pushed all the B ones to the front and the A ones to the rear, but we will cover our original basis and we see, okay, we found again the spin-like orbitals, even though we started at a pretty bad initial position. So this gives us some confidence that the local parity might be a good way to identify spin degrees of freedom, but this is a toy model. Let's see how this looks like in practice. Here we're looking at the closed configuration parabenzene molecule, which is known to be a diradical. So we know there should be 2 spin degrees of freedom in there, but they're not directly visible. And if we look at the local parities as they come out of a CAS-SCF calculation directly, then we see they're represented by this black line, which is basically everything up here. So this is the passive space, so we would expect that they're either fully occupied or empty. But even in the active space, we have massive mixtures of empty, singly occupied, and doubly occupied. So if we just looked at the results of the CAS-SCF calculation, we would think that there's actually no spin-like orbitals in there. But now we do our parity optimization procedure and we end up with this line that has this massive dip down here. We find in this new basis, there are 2 orbitals with a parity close to -1 and an occupation number of exactly 1. And they correspond to these 2 very nicely localized orbitals. They're basically just a 45-degree rotation between 2 of the original ones. So they're not that elaborate, but they wouldn't come out naturally out of the CAS-SCF calculation. So here we have 2 very nice spin-like orbitals that we wouldn't have identified with traditional means. We can also go to magnetic materials like the chromium iodine lattice and look at one monomer just for simplicity reasons. And again, if we do our parity optimization procedure, we identify there are 3 very nice spin-like orbitals. They're very nicely localized. They look very much like d orbitals. It's everything that we would expect, but we didn't put in any effort. We just took the result of the ab initio calculation, plugged it into our method, and this drops out naturally. So we identified the spin degrees of freedom for radicals, for magnetic materials. On to the next part. We know what the effective spin degrees of freedom are. So now we want to come up with a model description that treats these spin degrees of freedom just as these effective spin degrees of freedom, just as spin degrees of freedom in a path that is given by the fermionic environment. And for that, we turn to the old faithful, the Schrieffer-Wolff transformation, and try to massively generalize it so that we don't just use it for simple model materials where we do the analytic solution, but to plug in any kind of Hamiltonian and do an automated Schrieffer-Wolff transformation and know that the result that's coming out is still a very good approximation. So the Schrieffer-Wolff transformation, for those who are not familiar, is basically just a unitary transformation of the Hamiltonian with the aim to make it more block diagonal than it is initially. And that means we take the original Hamiltonian, we identify the part of the Hamiltonian that stays in a bit specific subspace. So where if you look at certain symmetries, I mean, in our case, it would be kind of particle number on certain orbitals. And we take the Hamiltonian that basically is already block diagonal with respect to the symmetry. And then we split off the part that is block off diagonal, so that connects these different symmetry sectors. And now we want to come up with a unitary rotation that removes, at least up to first order, this part V and replaces it with corrections that are still block diagonal, but which incorporate this effect of V. And the original idea was one does the unitary transformation, but because we can't really calculate this, it's a large many-body Hamiltonian, we do a Taylor series. But the Taylor expansion then also gives us a way of determining what the actual generator of this unitary transformation should be. Namely, it should be the generator that in first order, if we calculate the commutator with the block diagonal part, directly cancels out the block off diagonal part. That's easier said than done, because massive amount of equations, and it doesn't necessarily, there isn't necessarily always a solution, but we found a way to first think of this entire problem as a linear problem, so translate it basically as a linear algebra problem, and then to identify a way to come up, at least if there's not an exact solution for this, or basically if we treat it as a linear problem, if there's another exact solution to this equation, to find the best approximate solution that still gives us a generator that's small enough so that we don't introduce any kind of, or that we don't introduce any kind of big errors due to the Taylor expansion, but that removes the maximum amount of block off diagonality, so that the resulting model is vastly more block diagonal and can treat our system more like spins than the original fermionic Hamiltonian. Right. Of course, this again is some code and it does stuff automatically, but we want to check whether it agrees with the cases where you can do the Schrieffer-Wolff transformation analytically. So here we have the two classic examples where the Schrieffer-Wolff transformation has been done ever since the 50s and 60s. The single impurity Anderson model, the original example. We just do our automated system, our automated Schrieffer-Wolff approach, and look at the difference between the ground state energies of the original fermionic Hamiltonian and our effective Hamiltonian. And as the interaction goes to infinity, the difference between the ground state energies goes to zero even faster, because I've multiplied it with u already. So this is faster than 1 over u. And the other nice thing you can see here is this blue line is the parity, the local parity of this impurity side. And you see the local parity basically goes to -1 with roughly the same scaling as the energy difference. So if in the beginning we already see the local parity is rather close to -1, then we can also assume that our effective Hamiltonian is a good representation of the original one. And the same holds true for the Fermi-Hubbard model. So as the parity goes to -1 for each and every molecule, so this is the average local parity, the discrepancy between the original fermionic Hamiltonian and the spin Hamiltonian becomes also negligible. This again is model Hamiltonians. How does this look in practice? We go back to one chromium halogen. This time it's chromium bromide, but there's no reason why it shouldn't be chromium iodine. It's just we had the data for this, and we looked at the monomer. We first did our parity optimization. We found there are 3 nice spin-like orbitals, just as we expect. And again, this is bromide, not iodine. It's not the same molecule as I showed earlier. So we can go into this basis where we have 3 nice spin-like orbitals, and then do our Schrieffer-Wolff transformation. And now you have to pay a bit of pay close attention, because these are many different low energy spectra that I'm plotting here. So the black line, that would be the solution, the exact diagonalization of the original fermionic Hamiltonian. That's the baseline. That's what we want to emulate. The orange line would be the Schrieffer-Wolff transformation of this Hamiltonian. Already in the spin-like basis, but just the Schrieffer-Wolff transformation. That means the error that comes in here is just the error from the Taylor expansion. This error is pretty small, because the way we do our determination of the generator ensures that we don't take generators that are too big and that would introduce large errors, at the cost of maybe having a few more terms that we can't rotate out. Now the blue line is if we took our original fermionic Hamiltonian and just said, okay, we're now in the spin-like basis and we're doing a projection where we project out every term that connects Hilbert spaces where our spin-like orbitals are not singly occupied, two singly occupied ones. So terms that change the particle numbers in the spin-like orbitals. That's the blue line. The green line is the same approach, but for the Schrieffer-Wolff transformed Hamiltonian. You see, and then finally the purple line is if we start in the original CAS-SEF basis, take the three CAS-SEF orbitals that look the most like they would make sense as a spin-like orbital, and then do the projection there. You see the purple line is awful, whereas the other three at least agree very well on the ground state energy, and then there's some discrepancy for the spectrum high up between the projection and just the Hamiltonian and the full Hilbert space. But I'm also plotting the local parities in the different eigenstates. And you see, yes, there is a local parity of -3 because these spins, I mean, it's the average one, so it's -1 for the ground state. But then for the first couple of excited states, these are not spin-like. So we kind of shouldn't expect the projected Hamiltonian to describe these states. And then further up in the spectrum, again, there are states that are spin-like. So we have -1 here and here and here and here. So if we now condense this spectrum just to the states that lie in the Hilbert spaces that represent the Hilbert space in which we have these spin-like orbitals, then the spectrum becomes this. And now we see that basically also the projected ones lie on top of each other. That is nice as a validation for our spin-like orbitals. It's not so nice as a validation for the Schrieffer-Wolff transformation because it looks like it's kind of unnecessary. But if we zoom into the whole thing, then we see, but the blue line is still kind of 8 millihartry from the actual spectrum, whereas the Schrieffer-Wolff transformation stays within 2 millihartry, and kind of the effective Hamiltonian that we want in the end, the projected transformed one, that stays pretty much within a millihartry of the reference Hamiltonian. And not only that, the ground state is actually kind of within 10 to the -5 hartree. So the ground state energy is very well reproduced by the effective Hamiltonian. Yes, and I think that's all I wanted to tell you. There's a paper for it if you want to have a look in the details and convince yourself that it's a lot of effort and maybe not worth it to do it yourself. And yeah, that concludes my talk. Thank you very much for your attention.